Okay, now before we move on with the rest of these examples, I just want to go over a little that was then, this is now. So before, we had the case where we used the power rule to take the derivative of x to the n, and that was nx to the n minus 1. And what we've just seen is that we can use the chain rule to take the derivative of a function, g of x, raised to a power, and we bring the power down, and we raise that base function, as I call it, to one lower power, and then we multiply by the derivative of that base function. That's the case that we've just seen. There's also the idea that we had, if you take the derivative of e to the x, that is e to the x. E to the x is its own derivative. Technically, remember, we multiply by the natural log of e, which is 1. Now, supposing we needed to take the derivative of e raised to a function of x. The chain rule says we will rewrite the exponential, e to the f of x, and then we have to multiply by the derivative of that exponent, f prime of x. And then we learned a bunch of trig derivatives. I'll just use the sine function as an example. There were 6 of them that we had rules for. But the derivative of the sine of x is the cosine of x. Now with the chain rule, we can take the derivative of the sine of a function of x. And the chain rule says, okay, to take that derivative, we'll take the cosine of that function f of x, but then we have to multiply that cosine by f prime of x. So now let's use all 3 of these in new situations. So here's number 18. Let's see if I can keep that visible from your textbook. And notice that this is a product. So in addition to using the chain rule, we're going to have to use the product rule. So it's important that we recognize the first function and the second function in the product. Now I'm going to do a little sidebar and just take the derivative of each of these pieces separately. So the derivative, and now notice this is with respect to t, my input variable is t, based on the second situation right at the top of the page there on the right-hand side, to take the derivative of e to the negative 2t, I rewrite e to the negative 2t, and then I have to take the derivative of negative 2t, which is negative 2. Okay, and separately, what if I needed to take the derivative of the cosine of 4t? Well, based on what's in the bottom line there on the right-hand side, just up above, I have to think about the derivative of the cosine function in general is the negative sine function, so I'm going to take the negative sine of 4t, but then the chain rule says I also have to multiply that by the derivative of 4t, which is 4. And in this case, you may actually want to put the 4 out in front so that you don't accidentally confuse yourself in thinking that the 4t is multiplied by the 4. It is not. The 4t is inside the sine function. The 4 is outside the sine function, so that could come to the front. Okay, now let's put that together, and I'm going to move this down a little bit because otherwise I'm going to run out of space. So now overall I have a product here. So in order to find the derivative, dy dt, I have to take the first, that's e to the negative 2t, times the derivative of the second, and I'm just going to write it without actually taking the derivative yet, plus the second, that's the cosine of 4t, times the derivative of the first, and again I'm just going to write that I need to take the derivative without actually taking it. And now each of those ddt derivatives that I see there, I have done in the sidebar. So this right here, whoops, is done over here, and then this derivative is done right there. So I'm just going to make those substitutions. in my next line. So the derivative dy dt is the first times the derivative of the second. And what I found is that the derivative of the cosine of 4t is negative 4 times the sine of 4t. Then I have to take the second, cosine of 4t, times the derivative of the first. And based on what I did up above, the derivative of the first is negative 2e to the negative 2t. So I did put the negative 2 in the front. Again, that's a very small simplification, so you don't have to do that, although I will say it's important up here that you have these parentheses around the negative 2, because otherwise it's going to look like you're subtracting 2, which you definitely are not doing. So don't forget to put those parentheses in there. All right, very good. Let's try number 20. So here again, I'm going to take a little sidebar because I know that I have a product here once again. So I want to identify the first function and the second function. And hopefully you've gotten plenty of practice with these product rule derivatives so that you're starting to recognize them. So let's just take the derivative of the first here. So again, that's the derivative with respect to t, since t is my input variable. Now this is using the generalized form of the power rule, requiring the chain rule. So to take this derivative, I have to bring my power 3 down in front. I have to take that same base function, t to the fourth minus 1, and raise it to one lower power. That's the power of 2, 3 minus 1. And then I have to multiply that by the derivative of t to the fourth minus 1, which is 4t cubed, technically minus 0, but again, I don't have to write the minus 0. The derivative of the added or subtracted constant is 0. All right, now let me separately take the derivative of the second, and the second is t cubed plus 1 all to the fourth. So to take that derivative, again, I'm using the chain rule version of the power rule. So I have to bring my power 4 down in front. I have to raise my base function, t cubed plus 1, to one lower power, that would be to the third. And then I have to multiply by the derivative of t cubed plus 1, which is 3t squared, again, technically plus 0. So now that I know what the derivatives of the first and the second are, I'm going to go ahead and take the derivative of the whole thing. So h prime of t, using the product rule, that is the first, times the derivative of the second. Now the derivative of the second I have just figured out off to the side. So that's 4 times t cubed plus 1, all cubed, times 3t squared. I think I'm going to have to move down a little bit here. Plus, sorry about that, the second, that is t cubed plus 1 to the fourth, times the derivative of the first, and the derivative of the first I figured out in my sidebar, that is 3 times t to the fourth minus 1 all squared, times 4t cubed. So I have, whoops, I'm missing a parenthesis here. First times derivative of the second, and again, the derivative of the second I figured out in my sidebar, and the derivative of the first I figured out in my sidebar, so I just substituted them right in. So I'm using the product rule and the chain rule at the same time. All right, number 23. Here we have a function raised to a power. So this is the generalized power rule. And this function, for some reason, doesn't have a name, so I'm going to call it y. So dy dx, when I have a function raised to a power, I bring that power down in front. I raise that same base function, x squared plus 1 over x squared minus 1, all to one lower power, that would be to the second. Then I have to multiply by the derivative of this base function. Well, the base function is a quotient, so I have to use the quotient rule. That is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Okay, so again, this part is the quotient rule that I use to take the derivative of that base function. So there's lots of places where students might make mistakes on this. For example, forgetting about the quotient rule and taking the derivative of that fraction x squared plus 1 over x squared minus 1 as just 2x over 2x. That's incorrect. You have to use the quotient rule on that. Another common mistake is to forget to raise the x squared plus 1 over x squared minus 1 to the 1 lower power to have that square on there. Sometimes students forget that part. So again, just things to watch out for. All right, on to number 25. So this one, we know with trig functions, when they're raised to a power, that power is put in the middle between the trig function name and what we call the argument. And the reason for that is to make sure we don't confuse, for example, secant squared of x with the secant of x squared. But in order to help us understand how this is going to work, I'm going to actually rewrite them with the power outside of the parentheses there. So what I've done so far is rewrite the original function. I have not taken a derivative yet. Okay, so y is the secant of x squared plus the tangent of x squared. So here I have to use the chain rule on each of these because, again, my functions, each one of those is a function raised to a power as opposed to just x raised to a power. So the derivative dy dx, in the first case, I'm going to take the power 2 down. I'm going to raise what was already there, secant x, to 1 lower power, and I don't really need to write 1, but I'm going to put it explicitly there. Then, using the chain rule, I have to multiply that by the derivative of secant x, which is secant x times tan x. So that is the derivative of secant of x squared, and then I have to add to that the derivative of tan of x squared, and I have to run through the same process. So I bring my power 2 down in front. I raise the tan of x to 1 lower power, which is the power of 1, and then I multiply by the derivative of tan x, which is the secant squared of x. Now again, for my purposes on a quiz or a test, I would ask that you not simplify, but hopefully you can see that there's some nice simplification here. In the first term, we have 2 secants of x being multiplied together. So that would be 2 secant squared x times tan x. And in the second term, if I just rearrange the tan x and the secant squared x, reverse their order, I have another 2 times secant squared x times tan x. So I actually altogether have 4 secant squared x times tan x. So that is a simplified version of the derivative. Again, not strictly necessary, but if you had found the derivative and left it the way it is in the first line, and then looked in the back of the book for the answer and saw it written the way it is in the last line, would you be able to tell that those are the same? So that's why you might want to be able to simplify. All right, and then we have number 33. So again, I'm going to rewrite this. This is the cotan of the sine of theta all squared. So this is a triple whammy. We have a function inside a function inside a function. So this is like a triple composition. So to find the derivative, I'll call it y prime, or you could call it dy d theta. I have to bring my power 2 down in front. I have to raise the cotan of the sine of theta to 1 lower power. That's the first power. Again, you don't really have to write that. I'm just putting it there for those of us who are still trying to learn this stuff. Then we have to multiply by the derivative, and I'm going to just write it here that I need to take the derivative of the cotan of the sine of theta. So I brought my power down in front. I rewrote my base function and raised it to 1 lower power. And then the chain rule says I also have to multiply by the derivative of that inner function, cotan of sine theta. Now, how do I take the derivative of the cotan of the sine of theta? Well, there, the derivative in general of the cotan is negative cosecant squared. So I have to do negative cosecant squared of the sine of theta. Then the chain rule says I have to multiply by the derivative of the sine of theta. So again, I'm just going to write that here, that I need to take that derivative temporarily. So when I took, here, let me use a little color. When I'm taking the derivative of cotan sine theta, that itself requires the chain rule, because I'm not just taking the derivative of cotan theta, but I'm taking the derivative of the cotan of a function of theta. So I'm going to have to use the chain rule on that. Okay, so now I have one more piece to do. I have 2 times the cotan of the sine of theta times negative cosecant squared of the sine of theta. And last but not least, I have to take the derivative of sine theta, which is cosine theta. Now again, the parentheses, especially in this middle piece, are absolutely essential, because I don't want it to appear that I'm subtracting the cosecant squared. I'm not subtracting it, it's being multiplied. And the parentheses around the sine theta here are totally necessary, because I'm taking the cotan of the sine of theta, right? And again, you could potentially rearrange some terms and simplify a little bit, but it's not strictly necessary. And now our last little bit. This again is taken from your book. So we have already learned that the derivative of a to the x is a to the x times the natural log of a. So when we take the derivative of an exponential function, we rewrite the exponential function times the natural log of the base. Now here they go through a little exercise where they're showing you that if you rewrite e to the ln a for a, so I'm replacing the a with e to the ln a, and then raising a power to a power means you multiply the exponents. E to the natural log of a raised to the x is the same as e to the natural log of a times x. Then to take that derivative, I'm raising e to a function of x. So this is like e to the f of x that we had a few pages up. And to take the derivative of that, we would rewrite e to the f of x and then times that by f prime. That's what the chain rule says to do. So in these next 2 lines, that's what's happening. We're rewriting the base function e to the ln a times x. That's the e to the f of x. And then we're timesing by the derivative. That's the f prime of x part, matching what I wrote to the right-hand side. Now the derivative of ln a times x is just ln a, because ln a is like the slope on mx. So in the end, when I take the derivative of a to the x, that is a to the x times ln a. Now, if we had to take the derivative of a to the f of x, then we'd rewrite a to the f of x times ln a, and then the chain rule would say we also have to multiply that by f prime of x. So we can look at that as sort of, again, another case of how we have to use the chain rule. Up above, on previous page, we did e to the f of x, and now we're saying we could also take the derivative of a to the f of x.